To understand why bones break and joints fail, we must observe them at the scale of their smallest repeating units. We're deconstructing the human skeleton block by block, analyzing the microscopic components that dictate macroscopic health. We start with cartilage. This tissue operates under three strict physiological rules. It is avascular, aneural, and alymphatic. There are no blood vessels, no nerves, and no lymphatics. These pieces fit together in a specific sequence. Aggrecan complexes bind directly to a long hyaline backbone, and their negatively charged sulfate chains electrostatically lock on to the type 2 collagen. This creates a matrix that pulls in huge amounts of water, representing up to 80% of the tissue's wet weight. The hydration of this matrix facilitates the transport of gases and nutrients. Because there is no plumbing, chondrocytes must receive oxygen through diffusion. The water-dense gel acts as the transit medium, which is moved by intermittent physical compression during activity. The source of those diffusing nutrients is the perichondrium. This sheath of dense connective tissue encapsulates most cartilaginous structures and harbors the blood vessels required for this exchange. When you combine these standard rules, type 2 collagen, aggrecan, and a perichondrium, you get the baseline block, hyaline cartilage. Under a microscope, map the density of these molecular blocks by how they stain. The darkly stained rings surrounding the cells are the territorial matrix, highly concentrated with sulfated proteoglycans. Lighter intervening spaces are the interterritorial matrix, where collagen is more prominent. This baseline hyaline configuration is found in places like the respiratory tract, the growth plates of bones, and the surfaces of movable joints. Reliance on diffusion limits how thick cartilage can grow. Furthermore, the lack of direct blood flow results in a slow and often incomplete capacity for repair after an injury. The body alters this baseline matrix to meet different mechanical demands. To produce elastic cartilage, it takes the hyaline blueprint, type 2 collagen and aggrecan, and adds an abundant network of elastic fibers. This dark webbing provides greater pliability. You find this tissue where flexible shape and support are required, like the outer ear and the epiglottis. Fibrocartilage serves as a structural hybrid, mixing hyaline cartilage with dense connective tissue. Structurally, two things stand out. First, the matrix is packed with thick bundles of type 1 collagen. Second, the chondrocytes are arranged into narrow, axially aligned rows. Fibrocartilage lacks a perichondrium. That absence impacts how the tissue expands. Most cartilage grows via two mechanisms. Appositional growth happens at the outer edges, where new cells differentiate directly from the perichondrium. In contrast, interstitial growth occurs when existing chondrocytes undergo mitosis from within their lacunae. This expands the tissue from the inside out, forming small clusters of cells known as isogenous groups. Swapping type 2 collagen for type 1 and dropping the perichondrium trades shock absorption for tensile strength, creating a cushion suited for the intervertebral discs and the pubic symphysis. While cartilage relies on a pliable avascular gel, bone is a highly vascularized, rigid tissue built on a calcified matrix. The organic foundation is 90% type 1 collagen, laced with calcium-binding proteins like osteocalcin. The inorganic component, making up half the dry weight, is crystallized calcium hydroxyapatite. This diagram shows how that mineralization begins. Active cells release matrix vesicles rich in alkaline phosphatase. These vesicles create high local concentrations of phosphate and calcium ions, triggering the initial precipitation of hydroxyapatite crystals. Three specialized cell types drive this process. First are the osteoblasts. These builders utilize an abundance of rough endoplasmic reticulum to synthesize and secrete the uncalcified organic matrix, known as osteoid. You can see their activity here. These cuboidal osteoblasts line up along the existing bone surface, laying down a fresh layer of osteoid right before it hardens. As the osteoblasts secrete this matrix, some become trapped inside. Once encased, they transition into the second cell type, osteocytes. In reality, the mineralized matrix is a porous, living web. As osteocytes mature, they extend long dendritic processes through tiny microscopic tunnels called canaliculi. These processes connect via gap junctions, establishing a tissue-wide communication network. This allows osteocytes to share nutrients and act as mechanical sensors, detecting physical stress to signal for structural reinforcement. That reinforcement is carried out by the third cell type, osteoclasts. Unlike the builders, osteoclasts are giant multinucleated cells derived from the fusion of blood monocytes. A continuous, balanced push and pull between the matrix-building osteoblasts, stress-sensing osteocytes, and matrix-resorbing osteoclasts drives skeletal turnover. When an osteoclast begins breaking down matrix, it anchors itself to the bone surface using an integrin-based ring called the circumferential sealing zone. This graphic illustrates the specialized pocket created by that seal. The membrane facing the bone folds into a ruffled border, creating an isolated microenvironment that etches a depression into the bone known as a Hauschup's lacuna. Inside this pocket, the cell executes a two-part biochemical attack. It pumps protons into the space to dissolve the calcium hydroxyapatite, then secretes matrix metalloproteases to digest the underlying type 1 collagen fibers. This localized cellular activity dictates the macroscopic architecture of the skeleton. In compact bone, this remodeling process constructs highly organized cylinders of matrix. These cylinders are called osteons, or Haversian systems. Each features a central canal containing blood vessels and nerves, surrounded by concentric layers of matrix called lamellae, with osteocytes trapped between each layer. To ensure every osteon is fully perfused, the central canals are connected horizontally by transverse perforating channels, known as Volkmann canals. The microscopic requirements of the bone cells precisely dictate the macroscopic density, strength, and vascularity of the skeletal system. During embryonic development, the body relies on two distinct architectural blueprints to manufacture bone tissue. The first is intramembranous ossification. This is a direct conversion, where mesenchymal stem cells differentiate straight into osteoblasts. The body uses this method to form flat bones, like the skull. Long bones grow through endochondral ossification, a process of replacement where a hyaline cartilage model acts as the template. This replacement happens across 5 distinct histological zones within the epiphyseal growth plate. It begins with resting hyaline cartilage. The cells stack into columns in the proliferative zone, swell in the hypertrophic zone, and the matrix hardens in the calcified zone. Finally, in the ossification zone, osteoblasts invade to lay down the first layers of new bone. Endochondral growth exploits the rapid internal expansion rules of cartilage to create a temporary scaffold that the vascularized bone system then locks into place. The molecular architecture of these tissues dictates the physical progression of systemic disease. Osteoarthritis is a direct mechanical failure of the hyaline cartilage block. When the protective cartilage wears down, the physiological rules of the tissue work against it. Because the matrix is avascular, the chondrocytes cannot mount a sufficient healing response. The smooth surface cracks, ultimately exposing the highly innervated bone beneath. A herniated intervertebral disc is another failure of a specific microscopic variable. The outer ring of a spinal disc relies on the tensile strength of fibrocartilage. If those thick type 1 collagen bundles tear, the softer internal material can escape and compress the adjacent spinal nerves. Genetic errors in the bone matrix blueprints cause systemic collapse, as seen in osteogenesis imperfecta. This disease stems from a defect in the organic matrix. A genetic mutation prevents the proper synthesis of the type 1 collagen block, preventing the bone from withstanding normal mechanical loads. Conversely, we see the opposite effect in osteopetrosis. This pathology is a mechanical failure of the demolition crew. A genetic defect prevents the osteoclast from forming a functional ruffled border. The cell cannot resorb matrix, resulting in dense, unremodeled bone that chokes out the internal marrow space. If you master the microdiseases become predictable.